Okay, we're golden. Yay.
Now you got to bring in the tapes. Well, you know, this, all right, we approve. You look good. We're approving you. Okay. You have a younger sister or brother?
Me? No, I'm the youngest.
Okay. Sounds like a baby in the background.
I have some kids outside that are arguing. I can hear them even though I'm on the fifth floor.
Oh, that's fun. That's nice. All right, I see the GitHub. You want me to close? You want me to close the window with the names in it? Alma, Amaya.
No, you don't need to. Leave it on the side. It's fine.
All right, it's kind of big. Should I move it all the way to the left?
Yeah, you can do that.
Yeah, get them out of my way. Okay. All right, we're good.
Okay, so I'm just gonna,
Yeah, go past the book.
So syllabus, book, okay. So today, what are we covering? Are we covering
3, 4, 5, somewhere in there? I'll quickly go through 3 again. They won't even know that it was there. I don't think we get to 6, so just 3, 4, and 5.
Yeah, so we got 3, 4, and 5, and then let me just do one thing. Is Anvin here?
Hello, Anvin?
Yep, I'm here.
Good man. Awesome. Remind me to be nice to you at the end of the semester.
Okay, so there we go.
We'll give you extra credit and take it away from Ray. We'll change his 304 grade from last year. Okay. Yeah, we kind of did 3, but I want to fly through it again.
Okay, so
it's like it was a long weekend.
Okay, so this is 3. I'm gonna give up remote access.
To our friend.
Yes, I'm gonna give up remote access, and I'll leave the meeting.
So I'm approving. I'm approving it for Anvin. Okay.
Yeah. So Anvin's gonna ask. So I'm gonna leave the meeting. Good luck. Godspeed.
Wait a minute. Where's the notes? Okay. Leave computer audio. Let me see if I can lower this. No.
Okay.
Oh, choose one of the audio conference options. Computer audio, right?
Just ignore it. It's fine. Do you want to play specific videos?
No, not in this course.
Okay, so then yeah, it's fine.
Okay.
So yeah, I'm going to just leave the meeting now.
All right.
Yeah, Anvin has the rest of the controls. Can you switch slides, Anvin?
Hello, Anvin?
Yeah.
You get past the keywords. Take us past that. Okay. All right. So we were talking, well, you could leave it there. We were talking about the notion of a binary operation. Addition of natural numbers is a binary op because when you combine, oh, we only have 20 people? What happened? They stopped. You see? you make, oh, he's gone already. But Ray makes those nice lectures and nobody bothers to stay around. Okay. So addition is a binary operation. You combine 2 elements, 2 numbers, and you get a natural number again. But of course, subtraction is not. Okay. Are we early? People don't expect it to be on time after our experience. All right, Anvin, click again. Integers with respect to multiplication, yes, that's a binary op. Division is not. Rationals, hold on. Division of rationals, what do we say about that? As long as the second number is not 0. Okay. And where's Chu? Zhang? Zhang? Where are you? All right, he's not here yet. When, oh, All right, when anybody sees his name up on the tape up there, yell at me and I'll tell him that he was right last time. I overdid it with respect to when a number is rational and when it's not. Okay. All right, Anvin.
I hear you, Professor.
All right, so yeah, you're right. If indeed it's in the portion like 0.333, if it's non-ending and repeating, then indeed you were right, that it's rational. But the square root of 2 is not rational because you're not going to get repeats. So, okay, you won on that one. Shame on me.
It's okay, everyone makes mistakes.
All right, peace. Oh, length of a string, we went through that. We got 3 different ways to represent it. Big L of alpha, length of alpha, or put those bars up as we're used to seeing for the, usually at its absolute value. Here we're using it for length. Okay. Oh, we can click. We've seen all this. Empty string, we know what that is. Go ahead, one more time. Prefix, suffix, substring, we know those. That's good stuff for a midterm, we'll see. We'll put some easy questions like that on there. Oh, okay, click again. Subwords, every prefix is a subword, every suffix is a subword. Every subword is not a prefix. I think I got that right. And every subword is not a suffix. All right. All right. And of course, if you want to prove these things, we use induction. All right. Oh. Click again, Anvin. Concatenation of strings and concatenation of sets of strings. All right. We know how to do that. Go ahead. Oh, there you are, Chu. Yeah, so we know how to concatenate the sets. Give it another click. Cleany closure versus positive closure. The empty string is in one of them. I forgot which one. Is the empty string in the positive closure or is it in the Cleany closure of the set? Oh, we're going to put all of these on the midterm. You guys are coasting. You're taking it easy. I can see it. So the Cleany closure minus the empty string is the positive closure. Okay. Give it a hit, Anvin. All right, you got it. All right. Oh, I can do it too. All right. The language, yeah, we did that. Language expressions. We're going to be working with them all semester. Okay. Oh, and I can do it too, right? Yeah. The number of zeros equals to the number of ones. That's L2. All right. Okay. And L3, all strings omega such that omega is a binary string and omega equals the reversal of omega. All right, that's 0, 1, 0, 1, 0, 1, da, 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 da. Okay, so we know what palindromes are, decision problems, mommy, can I have ice cream? Yes or no. Optimization problem, how much ice cream can I have? So we've been through these. Okay. Language of a problem. This one, again, I know we went over it, but this is important. L sub prime, we want to represent problems in terms of languages. And that's the reason we studied languages. We don't care about languages. Well, we care about English so we can communicate. But the point is, we use languages to represent problems. So L sub prime, it's the set of strings of the form 1 to the p. So p is a prime, so you got 1, 1. Next week. All right, take it easy. Say hello to Camila. All right. Sorry, my cleaning lady was here. My place would be a mess without her coming by. So 1 to the p is a prime, you got 1, 1. And we said in language theory, we count like a dog or a horse. So that's rough, that's the number 2. Don't tell me it's 3. It depends on what code you're using. Rough, 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 the number 3, etc. 2, 3, 5, 7, 11, 13, 17. You got the idea, the set of primes. We already said it. 1 is not a prime number. Shame on you if you didn't catch that. What's the membership question or the membership problem? Given a language L and a string omega, is omega in L? Yes, if it is. No, if it's not. Oh, is the integer n a perfect square? I don't know. What's n? Tell me 1, I say yes. 4, I give you another yes. 16, 25, 36, 49, keep going. Those are all perfect squares. Okay. Yeah, optimization problem. Either optimization, careful, that covers minimization or maximization. So I want to get to California using a minimum amount of gasoline. Obviously, I'm driving. So, you know, what route should I take? And what kind of gasoline should I buy? All right. So maximum, how can I make the maximum amount of money with my investment? So optimization either means minimization or maximization. You got to specify which one. Okay. Traveling salesperson problem. NP complete. That'll be in your notes. I don't know if it's a few seconds or a few slides, but a problem is NP complete. That stands for non-deterministic polynomial. When we say a problem is NP complete, we mean it's difficult. We'll be able to do a lot better than that definition as time goes on. But for now, NP complete means it's damn difficult. That'll stick in your head. Okay. Yeah. What's the minimal tour between a pair of cities? All right. Go ahead, Anvin. If you want to convert an optimization problem to a decision problem, then let's see. The bottom there. Does there exist a tour through these cities? Yeah, make, oh my God. When this is a graduate course, then I usually take cities through India, and I have a lot of trouble. Undergraduates, I don't know. A lot of you have been around for years, so I could easily name a bunch of cities. So New York, Chicago, Pittsburgh, keep going. And you want to know, given these N cities that I'm enumerating now, is there a tour through the cities whose total cost is less than or equal to B, where B is an integer? So that's yes or no. So an optimization problem can always be converted into a decision problem. Okay? All right. So the language of a problem. Somebody's got the bongo drums out there. 46. We actually almost have the maximum here. The language of a problem is the set of yes instances of the suitably encoded decision problem. Okay.
Yes, sir.
Yeah, go ahead.
I had a question on the previous slide. So to convert a optimization problem into...
Wait a minute, wait, let's... Yeah, go ahead. This was the slide I think you meant.
Just my question was that in order to convert an optimization problem into a decision problem, we would have to know the answer to the optimization problem, right?
No. Hold on. Look at the bottom here. Does there exist a tour through these cities? You know, I was rattling off a bunch of New York to a New Yorker. Maybe you've seen the, what is that? It's on my wall. You know, what New Yorkers think of the planet. New York is a big blob of, you know, mass. It's the most important place in the world. And then you have other countries that, you know, right around the, of course, these days, New York is not so important. Does there exist a tour through these cities, New York, Chicago, etc., whose total cost is less than or equal to B, where B is some integer? We don't have to know the value of B. Somebody does. If you want to answer the question, you got to know, you know, what's the distance between New York and Chicago? 835 miles. I only know that because when I was 20, I hitched around the country. So I know how far, you know, the cities are from one another. But you don't have to know the answer in order to pose the question. You know, does there exist a tour through these cities whose total cost is less than or equal to B? That's a decision problem. Nobody said we have to have the answer to it, but that's how you would formulate it as a decision problem.
Okay.
What's your name?
Zio.
You're not showing. Okay. Oh, but Ray told me if I showed all of you, you wouldn't see me or I wouldn't see you. Who knows? All right, Anvin. Okay. So the language of a problem, the set of yes instances of the suitably encoded decision problem. Okay. So we know unsolvable problems exist. And we're going to prove the existence of quite a few of them later on in this course. I think for us now, it's too difficult to come up with unsolvable problems. That almost feels like an unsolvable problem. But I promise, give us a couple of months and we'll have the cerebral wherewithal. That sounds nice, to be able to make up our own. So one way to be sure of this result, that unsolvable problems do indeed exist, show that there are more problems in the world than algorithms. Okay. Yeah, we went through some of these. L is the set of languages L sub I, the first language, the second language, etc., etc. So if we can prove that the set of languages, that dark L, is all the different languages, and obviously we're talking formal languages. If you want to throw in English, Spanish, and French, be my guest, but we're not, this is not a language course as they would have at the UN. So the set of all palindromes, the set of all words that consist only of zeros, you know, those are languages. So if you can prove that's L, the cardinality of this set L, all the languages you can think of, if that's greater than sigma star is the set of strings, then we're in business. Yeah? So a language L is equal to a problem, and it lists the set of all languages. Okay. Okay, we're good. Take us on to the next one. I'll do it. Is that the end?
Sure.
Okay, take us to lesson 4.
Yeah, that's it.
All right, let's move on. Okay. And we're going to be done with the math portion. Then we go to the theory portion. Oh, no, we don't. You could look at those definitions on your own. I'm sorry, we both clicked. Let me keep my fingers off there. Okay. So we said this, there are more problems in computer science than there are algorithms. So, okay. So sets, wait. What happened here? 1 second. Wait, let me get rid of this. Go back to, the second slide. I clicked some that I didn't want to. All right. No, that's it. So we talked about sets in discrete math. Well, we talked about sets. Everybody does discrete math. Even your kindergarten teacher probably went through sets. Okay. So S is the set containing A and B. Let T be the set containing A, B, and C. Those little vertical lines, the cardinality of the set S is 2. That's how many elements it contains. I'm not telling you anything new here, I'm sure. The cardinality of the set T is 3. Okay. So to count the elements in a set, we need to establish a bijection. Oh my God. That's a one-to-one and onto mapping, okay? From the set into the natural, well, n prime, I'm talking about a subset of n. Yeah, n prime, there you go. And n is the set of natural numbers, 0, 1, 2, 3, etc. Okay. So if S is the set containing A and B, and you want a mapping from S to n prime, f of A equals 1, f of B equals 2. And I know you're supposed to start with 0. You know, for natural numbers, 0 is the first natural number. The trouble is we want to say how many elements are in a set, and so we're going to say 2. If you see A and you see B, that's 2 numbers. So I'm cheating a little. I'm saying we start with 1, f of A, but we know we're supposed to start with 0. So f of A is 1, f of B is 2. So the cardinality of the set S is 2. Okay, Anvin, give us a hit. I am very sad this year. Forget about the, well, we can't. It's the damn virus that's keeping baseball the way it is. You look at Yankee Stadium on TV, it's empty. What does it have? It's got 50 baseball players and a few dozen coaches. It doesn't look the same. I'm sorry. They got cardboard cutouts of people or Mickey Mouse or somebody. It doesn't look the same. All right, but there's Yankee Stadium on the right. And we don't need to actually count the elements to get their cardinalities. You can compare directly by mapping one set into the other. All right, here, this is straightforward. Let P be the set of people at Yankee Stadium. And I know, if you were in my 104 class, oh my God, is it M-A-U-R or N-A-U-R now, or where are you? You still sitting in the, well, you're not sitting in the second or third row, you're sitting in your house somewhere. All right, but P is the set of people at Yankee Stadium, and let C be the set of seats or chairs at the stadium. Then how do you know that P, the set P, is less than C? Somebody help. How do you know that the set P is strictly less than the set C? You don't want to count. You want to look at the stadium. How do things look? Oh, we're going to open up all your names.
There's sections, right? There's like the lower section. There's the nosebleeds. You know.
Oh, you know about that? The cheap seats. Yeah. When I was a kid, I was up in the nosebleed section. Sure. My uncle my father wasn't a baseball fan, but my uncle used to take me. So now I guess I have more money than I used to. So I've taken his son to a few games. Okay. But no, don't tell me about the different sections. Look at the whole stadium. When is P less than C?
If there are empty seats, then we know P is less than C.
And yeah, and everybody is sitting that's present. And when is P greater than C?
When you've got people standing around.
And all the seats are taken.
You got it. And P is equal to C if everybody is seated. And what the hell else? and there's no empty seats. All right, so you got it. So you don't need to count. All right. All right. Finite and infinite sets. A set A is finite with cardinality little n. That's a natural number. N is an element of cap n. So I don't know, 17, let little n be 17, and big N is the set of all natural numbers, 0, 1, 2, 3, etc. If there exists a bijection from the set A to the set containing 0, 1, 2, 3, and so on. A set A is infinite if there exists an injection, F from A, We got to move us over. Let me see if I can move us. That's me in the way, huh?
Professor, you're mute.
You're muted, Professor.
You hear me now?
Yep.
Ah, okay. All right. You can map the natural numbers into a proper subset of itself. Okay. F of n equals 2n. All right. So if you can do this, if you can map a set into a proper subset of itself, suppose I give you the set S contains A, B, and C. You all know there are 2 to the third or 8 subsets of that set. But I want a subset of the set containing A, B, and C, which is a proper subset of itself. Hold on. Okay, how about the natural numbers? And then consider the primes. So the prime numbers we've been over 2, 3, 5, 7, 11, 13, etc. And the prime numbers are a proper subset of the natural numbers. All right, I'm not making that too clear, but at least I said it right. Okay. The set of real numbers R is infinite. Okay. You got a mapping now from the reals into the reals. X plus 1, where x is greater than or equal to 0. Okay. And x if x is less than 0. Okay. I know I didn't make that clear. And sigma, consisting of A and B. Sigma star, the Kleene closure of that set, is infinite. All right. Somebody help with this next one. F is a function from the reals into the reals, and f of omega equals the symbol A followed by the original string omega. Somebody help. And I can't say I didn't have coffee, but my brain didn't click in. Why is F infinite? From reals into reals. Somebody rescue me from myself here.
Because there's more, there's infinite number of real numbers.
And f of omega equals A concatenated with omega. So you're mapping a set into a proper subset of itself. All right, we'll come back to that when I'm thinking a little better.
Is it because,
Go ahead.
Is it because there are infinite numbers of omegas in the Kleene closure?
Infinite numbers of strings. Don't say infinite number of omegas. Omega is omega.
Sorry.
Yeah. Okay, but I'm not describing it well, so I'll get back to that. Anvin, take us to the next one. Okay. Oh, finite versus infinite sets. A set A is of cardinality, oh my God, Aleph, A-L-E-P-H, the first letter in the Hebrew alphabet. We got anybody who speaks Hebrew out there? No? All right, usually I have one or two. So,
I do, Professor.
oh, okay, so you believe me, Aleph Sapnort, the first letter, all right, in the Hebrew alphabet. A set is countably infinite when it has cardinality alpha sub naught, okay? There you go. So a set is countable or denumerable when it is finite or countably infinite. So the set T containing A, B, and C, that's a countable set. Obviously, it's a finite set. It contains 3 elements. Countably infinite, the set is infinite, but there are sometimes sets that are bigger than that. So a set is countably infinite if you can establish a one-to-one onto mapping from the set in question into the natural numbers. And, well, I was going to say don't look at the last 2 lines, but you can see them. Give us an example of a countably infinite set that is not on the bottom of my notes here. We've mentioned it in the past 20 minutes or so. I want a countably infinite set, and I want you to prove it to us. Well, okay. I don't hear anything. So how about the primes? Why is this set of prime numbers a countably infinite set?
Because it's a set that belongs to all the real numbers also. It could be matched.
No. The real numbers are another issue. What do we want? If a set's going to be countably infinite, what do we need between the natural numbers and that set?
Well, you have to know which, if like the numbers, like you have to be able to count the numbers. Like if they ask you what's the first number, you could tell them.
Hold on, I think what you have to do in the future, and I got to get an attendance sheet with all your names. Actually, I ought to have it with your pictures as well. Let me see. But tell me your name before you give the answer. I want to know who I'm laughing at. Come on. So somebody just answer the question. What's your name first?
So my name is Li Fu.
Li Fu, okay.
Li Fu Tao. So my answer is, when it's countably infinite, it means that when people ask you what's the first number in the set, second number in the set, you can say it to them concretely.
So what you're doing is establishing a bijection, a one-to-one onto mapping between the natural numbers and the set in question. We agree that 1 is not a prime. So start with 2, the first prime number. 2 gets mapped into 1. Well, again, you're right. I should say 0. But when I'm counting, I don't like to use 0. I'm sorry, even though, you know, technically we would put it in there. So the first prime is 2. The second prime is 3, and so on and so on. So we had a one-to-one onto mapping between the primes and the natural numbers. And that could go either way between the natural numbers and the primes. Since it's a bijection, the mapping goes either way. Okay? All right, Anvin, give us a click. Oh, let A be a set. And enumeration of that set A is a surjective function. And I forgot, what's a surjective? Oh, I don't forget. I'm only joking. I always say that to get you to answer to help me out. But sur, from French, sur la table, on the table. So a function is surjective if the entire codomain is covered, if you will. All right. Okay. If F is also injective, then you have a bijection. So you could have an enumeration. That means you're counting without repetitions, or you can have an enumeration, a surjection, if you will, with repetitions. And what the heck are we saying? So if A is the set, and A contains ABC, then ABAC is an enumeration with repetition. You can see, of course, A is repeated twice, okay? And BCA, obviously, that's an enumeration without repetition, okay? If A is the set of even natural numbers, 0, 2, 4, keep going, and 2, 0, 6, 4, 1, 0, 8, they're both enumerations of the set A. Okay. The second one is a mapping f of n is 2 times n plus 1 when n is even, or 2 times n minus 1 when n is odd. So these are countable sets. Sometimes your enumeration repeats a number, sometimes it doesn't. Okay. Anvin, give us a hit. A is countable if there exists an enumeration of the set. Okay. 1 second. So the set sigma star, where sigma is a finite alphabet, okay, that's countable. The enumeration sigma star in standard order, A comes before B, B comes before C, and AA comes before AB. This is not like the yellow pages. What is it, AAA inspection services? I think that comes before A inspection services. I don't know. But the enumeration of sigma star in standard order, the alphabet is AB, and you see it down there. Epsilon comes first, A, B, AA, AB, etc. Okay. All right, Anvin, you can click. Cardinality of the rationals. The set of positive rational numbers, Q plus, is countably infinite. So we're claiming the set containing 1/3, 7/8, 15/16, and keep going as much as you would like. We want to prove that the positive rationals, that fancy Q stands for the whole set of rationals, and just the positive ones. So 0 is not in there. Okay. Countably infinite. Oh my God. We need to have a 1-to-1 onto mapping, a bijection between all the positive rationals and the natural numbers. I don't know, that looks tough. Give it a hit. Cantor's first diagonalization proof. So when you look at this, you know there's going to be a Cantor's second diagonalization proof, probably something else. So on the right, we're counting the natural numbers. Actually, we're showing an enumeration of the positive rationals. Across the top, 1, 2, 3, 4, keep going as long as you like. And across the, going down, 1, 2, 3, down towards South America. And don't go beyond because it's just a great sphere and you come back again. But keep going south. All right. So you want to count 1 as a rational number that's 1 over 1. You see it up there in the upper left. Then 2, that's 2 over 1. Ah, look at the 2 over 2. But 1 over 1 is equivalent to 2 over 2. It looks like we have an enumeration with repetition. Okay. Now, we're counting, and there's repetitions. So when you say 2 over 2 or 3 over 3, you're not giving me a number that's equal to 1. you're giving me a number that's equivalent to 1. And the example I always use, if you know I have a sweet tooth, so you want to be nice to me, you give me a quarter of a cake, you're giving me an ice cream cake. No, make it, apple pie. You give me a quarter of an apple pie. And I give you a sad face. That means I would like another quarter of an apple pie. You didn't give me half an apple pie. You gave me, what the hell did you give me? 2/4 of an apple pie. That's not the same as giving me half an apple pie. Why? Because it looks like you were trying to be cheap and I got sad, and so you gave me the other quarter of the cake. So equivalent doesn't mean the same as equal. Your discrete math teachers went into all that. They're equivalent, you know. No, I was going to go into examples with red wine, and you want to say they're equivalent. That means, okay, you don't specialize in drinking wine, so any red wine's as good as any other. So to you, they're equivalent, but they're not equal. I look at a beautiful Chateauneuf de Pape, and then I look at a Thunderbird, you know, some guy in the street, some homeless guy might be drinking. To me, they're not equal. You want to say they're equivalent, I'll buy it. So this enumeration of pairs of natural numbers, we're actually counting rationals. And 1/1, upper left, equate that to the number 1, okay? Come down and you see 1/2. Use the natural number 2 to count 1/2. Go back up and you see 2/1, 2/1. Use the number 3, okay? Go across to the right, 3/1. Use the number 4. What we're doing is we're enumerating natural numbers, excuse me, we're enumerating, what the hell are we enumerating? Rational numbers, but we're repeating some of the elements. 1, 1, 1, 2, 2, 1, 3, 1, 2, 2. We just repeated the natural number 1, its representation. 1/1, but we repeated when we said 2/2. So this is an enumeration of the rationals with repetition. So you can actually use the natural numbers to count the rationals. Now I hear you. I didn't count the negative rationals. Okay. There's a theorem that states a countable number of countable sets is countable. So we didn't count negative numbers. We got 4 quadrants we could consider. This is the right, what is that, right positive quadrant. Then you've got the left quadrant, minus 1/1, okay. You've got the bottom right quadrant, that's, what the hell is that? Minus 1/1, I don't know. And there's the lower left quadrant, negative. So, and just everything that's counted up here in the upper right, use every 4th integer. I'm sorry, every 4th natural number. 1, 1. What do I want? 1, 2. You got the idea. So multiply by 4 every result. And you could actually count all the rationals using just the natural numbers. Well, okay. All right, peace. Anvin? Oh my God. I was just about to say all sets are countably infinite. Where did this come from? So the reals are an uncountably infinite set. So we were comparing the, there's nobody sitting at Yankee Stadium. Well, you know, there's maybe 100 people. There's got to be a cleaning crew, you know, and they brought in some food for the players after the game. Who knows? But it turns out the real numbers, that's a set that's larger than the rationals. It's larger than the integers. So this set is larger. Okay. Oh, and this is what we said before. The union of a countable collection of countable sets is countable. Oh yeah, so you could prove that the rationals are an infinite set, but not all sets are countable. Oh my God. This is going to be a proof by contradiction. And oh, my discrete math students saw this proof. I know that. So the subset of reals over this bracket, it's the set 0, 1, where 0 is a closed set. That means 0's in that set, and 1 is open. So it's half closed, half open. So start at 0 and keep moving towards the positive side. Smallest steps possible. Up to 1, but please don't put 1 into that set. All right. So each x is real, such that x is between 0 and 1. 0's in the set, 1 is not. So this set goes up to 0.9999999, keep going. But you never get to 1. And this can be represented by an infinite decimal expression. So that's a bullet item on right below it. So x is x0, x1, x2. Okay. And this is a representation with repetition. And Chu, you were talking about the, you know, unending decimals. Yeah, those are.
Yeah, decimal expansion.
There you go. So these are rational numbers. 0.499999. Keep going. And we remember, I don't think we got this until middle school. So let x be 0.499999, and you want to prove that's rational. So multiply by 10. 10x is 4.9999. Keep going. So 100x is 49.999. So 100x minus 10x is 90x, which is 45. Chu, help me out. So what do I have? So x is 1/2, 0.5. That's all. There you see it. All right, so the reals are uncountable. Click it again, Anvin. All right, so this proof is a proof by contradiction. So first we assume the reals are countably infinite, and therefore we count them. Hold on, we're going to do that in a minute. So you got my virtual background. I should go back to my real background. I can reach the scotch. This class would be a lot more pleasant. I had enough scotch last night. The owner of the restaurant I go to sometimes, he treats me nicely. All right, so Cantor's second diagonalization proof. We want to prove that the real numbers are uncountably infinite. We said that's a proof by contradiction. So we assume that the set is countable and we run into a brick wall. We reach a contradiction. So assume the half closed, half open interval from 0 to 1. We said that means 0 is included, 1 is not. So 0 and keep going up to 0.999999, but you don't get to 1. All right, so it's countable. So here's an enumeration for the set. Point, so these are real numbers. The ordering doesn't matter. We don't care how we order things. So if it's a real number between 0 and 1, you got to give me a decimal point. So you see a big dot. F sub 0 equals a big dot, that's a decimal point. X00. Okay, I don't know what that is. I'm not even going to say it's a small rational. It's just some rational. I'm giving you an enumeration. X01, X02, keep going. And if you want to let them get larger, go ahead. F1, you got to give me a decimal point. So dot X10, X11, okay. So the second digit in every number here is a 1. I'm sorry, the first digit is a 1 in the second number. And then it's 1, 1, 1, 2, 1, 3, etc. Those are indices. You know, we're putting all the numbers down that have a 1 after the first, decimal point. And keep going until you get down to F sub n dot X sub n 0, X sub n 1, dot, dot, dot. So here they are. Maybe we lied. Maybe we're missing some of the real numbers between 0 and 1. It looks like they're all here, right? And on the left, F0, F1 through F sub n, that's the enumeration. The 0th real number, the first real number, down to the nth real number, where there's no bound on how big n is. So what the heck went wrong? We're trying to prove that the set is uncountable infinite, and yet we just counted them. And we're claiming they're all here. Then give me a hit. What's going on here? But now we're going to produce a real number, y sub nu, that's nowhere in that enumeration. You promised me that you were giving me all the real numbers between 0 and 1. I don't want to keep saying half closed, half open. You know that's what I mean. But if you're giving them all to me, I shouldn't be able to find a new number. But look at this. Y sub nu. Here's a new number. I withheld it from you. It's between 0 and 1. But look at this. Y sub 0 is not equal to X00. If it's not equal to X00, then it's nowhere in the listing. So Y sub nu is not equal to decimal point X00, X01. You know, if I give you 0.189 and then I tell you 0.289, they're not equal because they differ in the first number. Okay, so Y sub nu is not equal to the first number in our listing. Oh, that's cool. Might be equal to something else. We're not giving up yet. Y sub 1 is not equal to X11. So the two numbers differ in the second digit. And keep doing that. Keep making this Y sub nu different than every number in the listing on the previous page. If it differs in every, by one digit in each of that number, the numbers in that infinite listing, therefore Y sub nu is nowhere to be found in our enumeration. But you promised me that we had them all, but we didn't. We were able to find a new number that was nowhere in the enumeration. Therefore, the reals must be larger than the natural numbers, larger than the integers, and what we were trying to prove when we started this proof, larger than the rationals. So give us a hit, Anvin. So the reals are uncountable. We tried counting them, but we reached the contradiction. We just found, By the way, some mathematicians hate this kind of proof, because when do we get the number that's not in our listing? You know, how could, you got to give me an infinite number of steps. You're not allowed to tell me you found a number that was nowhere to be found in the listing that we gave. It's never going to happen. So this is sort of an infinite process, which means we don't have an algorithm. So we reach the contradiction, our assumption is false, the interval from 0 to 1 contains an uncountably infinite number of numbers. So the reals are uncountable. We were just proving that the reals between 0 and 1 are uncountable. So obviously the whole set of reals is uncountable. Okay. This one is good for homework. If sigma is a finite non-empty alphabet, you know, we went through alphabets the past few classes, you know, the set of integers, the set of, letters in the alphabet. P, that's my fancy P. It's supposed to stand for power set. So start with an alphabet sigma, A through Z if you like. Then sigma star is the set of all strings using letters from the alphabet sigma. And then power set of sigma star is the set of all strings that are subsets of sigma star. Okay? And this proof is going to be somewhat similar. So see if you could prove that rho of sigma star, the power set of the Kleene closure of a set, is an uncountable set. So it is larger in cardinality than sigma star. So sigma star, the set of all strings over some alphabet. That sounds like it's infinite. But then the set of all subsets of strings from an alphabet is a larger set. Okay. So go over this. Maybe we won't see it until the midterm. Try not to think about this. All right. All right. So we've been arguing about the equivalence of languages and problems. The number of problems in the world is greater than the number of languages. Therefore, unsolvable problems have to exist. Right? And I don't mean I can't pay my tuition because I'm broke. I mean problems in computer science, not problems in life. Life always presents unsolvable problems. Right? We know that when we go outside and we're wearing these silly masks. Okay. Anvin, give us a hit. Hold on.
Still.
I had a watch when I came up. My computer, all right. My computer's covered with the tapes. Yeah, I think we're going to make up a new rule that the drinking scotch is okay in class. We'll see. All right, I'm just drinking water. I don't drink as much scotch as I say I do, but that's okay. We're up to lesson 5?
Yeah, that was the end of lecture 4.
Okay. All right, give us a click, Anvin. Oh, yeah, we went through all that. Okay. And review, yeah, we went through all those things. Primes, decidable problems, optimization problems. Go ahead, give us another hit. Mommy, I want ice cream. No, no, no. Oh, I think we're going to skip this one. We'll come back to it another time, this lesson. Take us to, what's next, 6? Okay. And hit the little icon for PowerPoint. Okay. Turing machines. All right. Oh, these are from the last. Okay. All right, Turing machines. We'll start. Usually, you're right, I skipped lesson 1. We had a Turing machine, and we actually had a rather difficult Turing machine. But now we're just going to take easy examples. We're going to play it by ear. So a formal definition. All right. So we're going to assume some finite input alphabet. Okay. That doesn't seem hard. And sigma, the alphabet is A1, A2, A3, up to A sub k. Every Turing machine has a finite non-empty set of states. The set of states Q, Q0, Q1, up to Q sub n. We got some distinguished initial state. Oh, I don't know. Q sub init. And yeah, I usually just assume it's Q sub 0. So that's our initial state for our machine. And we said, if you've never taken theory or this kind of stuff before, you think of a soda machine. You get to it, it's empty. That's the initial state. Unfortunately, and I think this was my downfall, when I was a freshman out at Stony Brook, I was studying in the basement, and there was a soda machine and a candy machine. I don't know what happened. I think I was pressing the candy machine. And for every time I pressed, the chocolate bar came out. I didn't put any money in. It was stuck in Q0, but candy bars came to me as if from heaven. I think that's where I got my belly from. But usually Q sub 0 means there's no money in the machine. Then you put a quarter in, you're in state Q sub 25. We said City College is more expensive than NYIT. When I moonlight over there, it's actually $1.75 for a Coke. In City College, it was $2.10. That's how I went broke. All right, so, okay, it's a definition for a Turing machine. Go ahead, click. All right. So the alphabet is A1 through A sub k. Identity, K plus 3. Read, write. You're, in English, in America, when you say that someone's not too swift, you're kind of saying they're slow. So the way you would insult somebody, well, you got to be, don't insult anybody, but you would say, that guy can't walk and chew gum at the same time. You know, his brain can't keep track of 2 different actions going on. You got to move your legs. I don't know. Is that your autonomic nervous system? I don't know. But he can't walk and chew gum at the same time. You got to move your teeth. You got to move your legs. Who knows? In our book, oh my God, who is he? What's the author's name of this book? I've only used it for 100 years. Yeah, I don't even have it. Ray, well, Ray's not here, but.
Gregory Tyler.
What's his name?
Gregory Tyler.
Okay. No, not Tyler. You got a different book. All right, we'll get there. But in the text that I had chosen, the way a Turing machine is defined, the machine can either move, so the head can go left or right. I'm doing it the way it's correct for me, so you think I'm going backwards. That's okay. Or it can write an A, write a B. If it needs to write and move, that's 2 moves. First you write, then you move, okay? So, all right, so careful. When you get to JFlap, we're not there yet, we're moving. JFlap actually permits a move to consist of a move and a write. You can do both things. So those are smarter Turing machines, if you will, okay? So here's the possible Turing machine actions. And again, I don't think it's too confusing for you. If on a midterm I say the Turing machine can both move and write, or it can only move or write, you should be able to put up, you know, handle that kind of complexity. That doesn't sound hard to me. If you're an upper sophomore or a junior, you can handle that. So possible Turing machine actions. Capital L. When you see capital L, again, this is Taylor's textbook, Taylor. In Taylor's book, capital L, move one square to the left. That's the way you would designate it. Capital R, the head, you know, you've seen the pictures in my notes. The head, capital R, move one square to the right. Okay. B for blank. Okay. Erase whatever's on the square that's currently being scanned. So B stands for, you know, an eraser. You're erasing one cell. All right. A sub 1, erase whatever is on the square currently being scanned, and in its place, write A sub 1. We're going to have symbols that we write on this Turing machine tape. Okay. It'll get pretty fancy. We can sort. We're going to do things you wouldn't think we could do. You're probably going to throw your laptops away. When you see how powerful a Turing machine is, you're going to say, why did I spend $1,400 for a, you know, a Mac laptop? You didn't need to. You could have done all your homework. It just would take 1,000,000 times longer, but you could have done it. So, all right, A sub 1, we said erase whatever's on the current square and write the symbol A sub 1, which is, I assume, has some meaning. A sub 2, erase whatever's on a square now and write A sub 2. Up to A sub K, and I bet you know by now what that stands for. All right, Anvin, give us a hit. All right. Turing machines formally. Again, usually I've done an example or two before this point, but I didn't get there yet, but we'll get there together. So this is a Turing machine instruction in Taylor's syntax. Again, every textbook, you're going to use different letters. You don't want to be accused of cheating, so you make everything different. What do we have? 4 things. A quadruple. Okay. In those brackets, Q sub I, we're in some state. Q will always stand for state. It'll have a subscript, Q sub I, Q sub J, Q sub 0, I don't know, but there's a Q. Sigma, we're going to write something. Well, actually, write or move. So it's an action that's being taken. You're either going to write something, or you're going to move left, or you're going to move right. Okay. Wait a minute. In a state, scanning a symbol. Let me take it back. It's a symbol. Sigma is some symbol. I don't know what the symbol is. Whatever you're seeing. All right. Do some action. The action can be a write, W-R-I-T-E, or it might be a move, capital L, capital R. Or capital N, don't move, stay where you are. Sometimes we use capital H, halt. Okay, Q sub J, hold on. Q sub I is the state you were in when you started the move. Q sub J is the state that you're in when the move is done. So you see 4 things here, that's a quadruple. If it's a different textbook, and again, since we're going to be using JFlap as well, it'll be a 5-tuple because you'll be moving to the right or left and you'll be writing. So that's 5 things. All right, so you won't get confused. So you should be reading chapter 1, which goes through, chapter 0 is going to take you through the math we were talking about. Chapter 1 will start with a gentle discussion of Turing machines that we're looking at now. Okay. And then when we look at other Turing machines, you know, maybe the notation will be 5 tuples. You can handle it. It's fine. So Q sub I, the current state, sigma. The elements of sigma, in other words, the alphabet that the Turing machine can play with, union B, the blank symbol. Either you're erasing something, or there's a blank on the square, and you'll know what to do. And we got K plus 3 actions that we can take. But I don't know what K is. It depends on how complicated the algorithm is. Q sub J, next state. And by the way, the next state that you're in, Q sub J, might be equal to Q sub I. So you might have a while loop. If you think about Turing machine programming as simple programming in you know, C++ or whatever, Fortran, it's not going to be that different. So, okay. So possible machine actions. Write any of the symbols A1 through A sub K. Remember, we had a problem. We didn't solve it. We wanted to check if a string had the format A to the N, B to the N, C to the N. We were able to check parentheses, you know, with the number of left parentheses equal to the number of right with a pushdown automaton. But when it came to checking if a string was of the form n copies of A, followed by n copies of B, followed by n copies of C, a pushdown automaton was not strong enough, was not a powerful enough model. It didn't have the wherewithal to do that. But with a Turing machine, we're going to be able to do that, okay? So we can write any one of A, B, or C, whatever we need. Make your alphabet as extensive as need be. Move left 1 square to the left. We said we'll use a capital L. Move to the right 1 square, capital R. Erase symbol being scanned. I don't know, you got a little A on the tape in some cell. If you write a B over the A, that means you're erasing it, okay? And you can have auxiliary symbols. Help, you know, these are help symbols. So you want to check if a string has the form A to the N, B to the N, C to the N. Maybe you see an A, write a star over the A. Okay, that's nice. And now move to the right and you see 1,000 more A's. Leave them alone. So the first one, you saw an A, you wrote over it with a star. See a second A, while the symbol you're scanning next is an A, move to the right 1 square and stay in the same state. And do that 999 more times. So I have 1 star, followed by 1,000 A's, and now I come across a B. Oh, what the heck. See a B, right over it with a star. And by the way, you better change states. When you were looking for A's, maybe you stayed in 1 state. Then later, when you're scanning B's, see a B, write a star on top of it. See the next B, leave the B alone, and keep moving 999 more squares. And finally, you see a C. Aha! See a C, write a star on top of the first C. What do we have now? We have star, 1,000 A's, star, 1,000 B's, star, 1,000 C's. Now, move to the right. We see a C. Hit it with a star. So now what do we have? Well, you know what we have. Star, 1,000 A's, star, 1,000 B's, and then 2 stars and 999 C's. Go back where? Ah, I forgot to say something. Capital B is a useful way to mark the beginning of your tape. Put the blank at the beginning of that word. Okay, the word was A to the N, B to the N, C to the N, before you started marking things up. So at the left end of this Turing machine tape is a blank. So at the right end where we're up to, I see 2 stars. Go left until you hit the blank. Then do it over. Do what? You hit the blank. Move right, you're going to see a star. Why? You wrote the star when you saw the first A. I move to the right again. You see another A. Write a star. Ah, blank, 2 stars, 998 A's, 1 star. What do we start with? I think it was 1,000. Did I have 9? No, I didn't have 1,001. So the point is, we keep going back and forth across the tape, each time marking off an A, a B, and a C, and writing over them with a star. After 1,000 trips back and forth, I now see blank, 1,000 stars, 1,000 stars, 1,000 stars. Like I was hit by a big fist. Boom. I saw stars in college once in a gym class. The weights just fell down on my, where was it, my hand? And everything was white. So the point is, well, we're not going to talk about my gym class. We've started out the entire string, and there's nothing left. It's a blank, 3,000 stars, and let's put a blank on the right end as well. Since the letters A, B, and C all ran out at the same time, you can be sure that the string had the proper syntax, which was A to the N, B to the N, C to the N. If when you're done with all this, suppose there's no more A's left, but there's still a B on the tape. Say no. What was the question? You remember, Mommy, can I have ice cream? That was our first decision question. So now, is the number of A's, B's, and C's equal? No. We erased all the A's, and now there's 1 B left. There weren't supposed to be any. We were supposed to have 1,000 of each. If you still have a B on the tape, the syntax of the string was wrong. So now suppose the A's are gone, the B's are gone, but you still have 2 C's left on the tape. Then the original string was A to the 1,000th, B to the 1,000th, C to the 1,002nd. So doing one step at a time, we can see how a Turing machine might, what's the word, not judiciously, but exhaustively check a string for syntax. Okay, so hold on. I think there's 3 minutes left. Hold on. We want to hang in there. So possible Turing machine actions. I think we got this down. Anvin, give us 1 click. All right. Turing machine instruction formally. Q sigma action Q sub j. So we said that's a quadruple. Q sub I, current state. Sigma, the element of the alphabet, but you're in. So B for blank is not really part of the alphabet. It's part of the machine alphabet. It's an auxiliary alphabet. It's not part of the input alphabet. So B, the machine has that symbol. A, B, and C, that's your alphabet. You're trying to solve a problem. K plus 3 actions. And we said this, write any one of A1 through AK, move left a square, right a blank, a square, erase the symbol being scanned with a blank. And we have other auxiliary symbols. We were using star. Maybe you want to use X to cross out an A, Y to cross out a B, and Z to cross out a C. So there's an auxiliary alphabet. Anvin, another click. Okay. Same number of A's and B's. Give me a couple of minutes. Click again. Anvin, we want to do this problem. All right. So we're just going to finish this, then we're happy. So this is a Turing machine using Taylor's notation. His machines don't walk and chew gum. Take your pick. So we're going to do one or the other. We want to know if omega lies in L of M. L of M, M is the machine. L of M, the language of the machine. Look at the bottom, figure 1.3.1. We want to know if a string omega has the same number of A's and B's. Using a Turing machine, we're not using, we're not going to count the red jelly beans and yellow jelly beans. We have a Turing machine. We're going to start at state 0. Look at the middle of the left side. You see a big arrow coming in. I don't like his notation because, I don't know. How do you know you're in Q sub 0? But okay, that's the start state with the big arrow. We want to know if the string has the same number of A's and B's. Okay. If it has an A, we're going to go north. If it has a B, we're going to go south. If it starts with a blank, we're probably going to accept. And by the way, we accept by writing a 1 on an otherwise blank tape. We reject by writing a 0 on an otherwise blank tape. All right, let's start. We got 16,000 A's, 16,000 B's, randomly organized here. The first symbol's an A. Go north. Okay. So you're on your way to Chicago. That's going north. And star out the A with a star. What the heck? Okay. So you just crossed off 1A. You're in state 1. Obviously, no chewing and walking at the same time. So in state 1, you see a star. Why do you see a star? Because you just wrote a star when you were leaving state 0. We said Taylor's machines don't move and write at the same time. So going from state 1 to state 3, write the star, and, leave it alone and move to the right. Okay, you see a star? This might not have been your first time through the tape, or this may not have been the first symbol that you processed. Therefore, you might see a few hundred stars. Go see a star, move to the right. See another star, move to the right. See an A, move to the right. Why are you moving to the right? Because we're only going to match one A at a time with a B. We're not going to mark off another A now. How the heck would you know how many A's you've encountered so far? So you're in state 3. This is where I said, think of it as a while loop. While you're in state 3 and you're seeing a star, stay in state 3 and move to the right. If you're in state 3 and you see an A, rewrite the A and move to the right. Okay, finally you see a B. You better do something different. You want to match the B to the A that came as you were leaving state 0. See a B, star it out. You've seen one, imagine we just started. Then you've seen 1A and 1B. Go to state 5 and go left, right? What was it, Harley? Really? Go west, young man, go left? Oh, go west. We're going to the right. Now we're going left. Why the heck are we going left? We want to get back to the beginning of the tape. So we got back to state 0. See a B, star it. Okay, now you've matched 1A, 1B. See a star, you just wrote a star. You're going to see it now. Go from state 2 to 4 and go to the right past the stars and the B's if this is your 1,000th trip across. Finally, after all that movement, you see another A. Then go to state 5, and from state 5, you're going to keep moving left until you get back to state 0. Eventually, after 2,000 moves, I don't know how many, you're going to see a blank. You got back to the left end. Go left, And state 6, Taylor is very neat, tidy. He wants you to erase everything you wrote. You were writing stars. The dance between state 6 and 7 is erasing stars and putting in blanks. All right. Eventually, all the stars that you wrote, you had a broom and you kept sweeping them over. You get to state 6 and there's no stars left. You see a blank, write a 1 and go to state 8 and halt. At this point, you've erased all the stars that you wrote and there's nothing on the tape, just blanks. It's time to go home. The string is accepted. All right, go in peace. Study this example carefully. So this is a Turing machine that can move or it can write. It can't do both. When you use JFlap, you'd be able to solve this problem a lot faster. It would only take you, 17 hours instead of 34 hours, instead of the nanosecond that your laptop takes. But we're going to use it. We're not looking for speed. We're looking for understanding. All right, peace. Finish this example at home. Make sure you know what the heck is going on. All right, so we talk about recognizing a language. All right, peace. So we're in this chapter. Keep reading. Look at the problems. All right, I'm not running away. Hang in there. I'll be back in a minute. You got questions? I'm around. Let me get some bourbon.